Welcome to the Explainer. So, if you've ever watched a massive Starship launch and, wondered how on Earth we're going to push heavier and heavier payloads faster into the cosmos, well, the answer actually lies in a complete redefinition of modern thermodynamics. Today, we're unpacking exactly how SpaceX's Raptor engine is absolutely shattering the established ceilings of fuel efficiency. We're going to look really closely at the data and the raw mechanics behind this, frankly, massive shift in chemical propulsion. Okay, let's dive into this. Consider this massive statement right from our source text. Everything you were taught about the limits of rocket science is officially obsolete. Seriously, for decades, aerospace engineers just kind of believed they had essentially maxed out what chemical propulsion could do. But as it turns out, traditional engines were actually leaving a tremendous amount of potential energy right on the table, wasting massive amounts of it purely due to their design. So the Raptor engine isn't just some, minor iterative improvement. It is actively rewriting the laws of thermodynamics through a radically different mechanical process. Section 1, the thermodynamic limit myth. Think about it for a second. Why did traditional rocket engines, even incredibly powerful ones like the RS-25, hit a complete plateau? For years, the entire aerospace industry just accepted this as a hard boundary. We all just assumed we'd extracted every single ounce of thrust possible from chemical reactions. But here's the catch. That plateau wasn't dictated by the chemistry itself. No, it was dictated by the mechanical systems processing it. The ceiling existed not because the fuel lacked energy, but because those older architectures simply couldn't utilize it all. Let's move to Section 2, the open cycle problem, and see how this builds. The real villain of our story here is the fundamental inefficiency inherent in the open cycle design. See, to drive massive turbopumps, traditional engines actually bleed off and just dump unburnt propellant straight overboard. It's essentially throwing away perfectly good fuel just to keep the engine running, which is exactly why those legacy systems hit a thermodynamic limit in the first place. The Raptor, however, completely flips the script by shifting entirely to a closed-loop system. Instead of venting that precious exhaust, it captures the maximum amount of power by making absolutely sure nothing gets dumped. Which brings us to Section 3, full-flow staged combustion. Now, what's really interesting about this slide is how it translates some pretty heavy jargon. At its core, full-flow staged combustion really just means treating the entire rocket engine as a giant closed-loop heat engine. It's this absolutely brilliant architecture designed specifically to perfectly stop propellant waste. By ensuring all the drive gas used to spin the turbopumps is eventually routed right back into the main combustion chamber, it maximizes energy extraction. Literally every fraction of chemical potential is put to work generating thrust rather than just being vented away as a sort of mechanical tax. Let's break down how this mechanical flow actually works step by step. First, propellants enter the system. But instead of splitting off a fraction to just be wasted, Step 2 shows how they are used entirely to power the turbopumps. From there, for Step 3, all of those incredibly high-pressure, hot exhaust gases are directed straight into the main combustion chamber for the final ignition. There's no dumped exhaust, zero wasted mass. All the mass and all the energy are conserved and expelled precisely where it matters, straight out the back of the engine. Moving on to Section 4, the subcooled methane advantage. And this brilliantly illustrates exactly what makes this whole setup tick. The chemistry is what makes this closed-loop design viable and fully optimized. By utilizing subcooled liquid oxygen and methane, the propellants become incredibly dense. Packing significantly more fuel into the exact same volume is what actively allows the system to bypass those traditional thermodynamic limits we talked about earlier. It's this perfect, beautiful marriage of dense, subcooled methane and a closed-loop combustion cycle that results in the Raptor achieving its completely unprecedented power-to-weight ratio. Let's zoom out a bit for Section 5, redefining deep space exploration. Because you see, this isn't just about elegant engineering for the sake of it. High-efficiency combustion is literally the critical mechanism for sustainable deep space exploration. When you're traveling between planets, every single ounce of mass matters. If we just rely on legacy open-cycle engines that throw away unburnt propellant, the payload fractions for something like a Mars mission simply do not close. Stopping propellant waste and maximizing that energy extraction is the exact prerequisite that makes sustainable interplanetary travel mathematically possible. So the thermodynamic limits of the past have been bypassed entirely. Between subcooled methane and full-flow staged combustion, the old rules of rocket efficiency just don't apply anymore. Now that the ceiling has been well and truly shattered, what are the actual new limits of sustainable deep space and interplanetary travel? I mean, if we are finally extracting maximum energy without a single drop of waste, just how far and how fast can humanity go next?